First, I want to thank the organizers for the invitation. I'm very happy and great honor to give a talk here. So today, there are 3 parts in my talk. So in part 1, I'm going to give a very brief introduction about optimal trend plot, but I know many experts here as well. And then we are going to introduce optimal partial trend plot. In the optimal partial trend plot, there will be the free boundary comes out. So second part, I'm going to introduce some recent result on the regularity for free boundary. And then last part of my talk, we are going to look at a slightly different model of optimal trend plot. So in which we have the singular set. But in fact, it turns out to study the regularity for the singular set is very similar to the study regularity free boundary. So that's in the last part. All right, let's see what is the optimal trend plot. It can be described in the following way. So imagine we have an initial domain omega, and we have a target omega star. And over omega star, we have the probability measure f and g. So that means the total mass is balanced is equal to 1. And we're trying to move everything from omega to omega star by a transport. So transport, that means it's a mapping T from omega to omega star. And this mapping T has to be measure preserving. So measure preserving, that means it's not only preserve the total mass, it also preserve the local mass as well. So in mathematics, that means if you consider a subset E in omega star, then the measure of the E is equivalent to the measure, is equal to the measure of the pre-image. So if this equation is true for arbitrary subset, then the mapping T is called measure preserving. Right? Now, given a cost function Cxy from the product space to R, so the meaning of the cost function, it depends on your application. It could be how much money it costs you if you want to transport a single mass from location X in omega to the location Y in the omega star. It could be how much money, it could be how much time, how much energy, it depends on different kind of background. Now, once we have the cost function, now you are using the mapping T to finish your job. The total cost will be this functional. Okay, I mean, in the discrete case, it's just you adding all the cost. In the continuous case, we do an integration. And optimal trend plot is trying to minimize this total cost among all the measure preserving mapping T. Okay. As we can see, such a problem is actually heavily depend on cost function. So different kind of cost function, we have different kind of application, and we have a different property for a solution as well. So the original cost function asked by Monge in 1781, it's very simple. It's xy Euclidean distance. It looks very simple, but however, it gives us a lot of trouble. I mean, it's not very nice cost function in mathematics. Why is that? Let's consider in 1 dimension, in R1. And you imagine we have 3 points, and we're trying to put 3 points into 3 holes. Okay? If the cost function, you choose a cost function with the power p, and this p is greatly larger than 1, then you can verify it's very fundamental. The best way to finish the job is first one goes to the first, second one goes to second, and last one goes to last. It's parallel. Now, if you change the power p to p less than 1, then again, you can verify. I mean, it's a R1, it's 1-dimensional. The best way to finish your job is the first one goes to the last, and the last one goes to the first. So you have to flip the order, okay? And the trouble is p equals 1, right? So p equals 1, it doesn't matter as far as it's 1-to-1 mapping. So that means in mathematics, we do not have uniqueness. Okay, as far as it's 1-to-1 mapping, the total cost is always the same. So I mean, no uniqueness, it gives us a lot of trouble as well. For sure, we can put a log function. If you put a log function, this cost function has application in reflector design problem. So reflector design, I mean, I just very briefly introduce this. So imagine we have a point light source at the origin, and it emits along different direction. The light's going to emit from a different direction. And over here, we have a hypersurface that is a mirror. So that when the light touch the reflector, it will be reflected downwards and they eventually illuminate a target. Okay. So the problem is if we have all the initial data and we have all the target data, and how can we design such a hypersurface? So that's called reflector design. And we can formulate such a problem into optimal transport with a cost function given by the log function. And we can also consider a log of the inner product. So this cost function has the application in geometry that is called Alexandrov problem. It's a duality, it's a dual to the famous Minkowski problem in convex geometry. But however, from the PDE point of view, our theory cost function is quadratic. Okay, why is that? Probably we already heard many talks in this week. So why do we prefer the quadratic cost function? Because if the cost function is quadratic, then Brenier told us that such an optimal mapping T not only exists and is unique, and moreover, is given by a gradient of some convex potential function. Okay, it's pretty nice. And because this mapping T is given by the gradient of the U, and the gradient U will push forward the initial density function F to the target density function J. So therefore, by using the integration, the change of variable formula, and we can calculate what's a Jacobian of this gradient. So Jacobian of the gradient, that's exactly determinant of the Hessian. So that's why we end up with a Monge pair. So the PDE is determinant D2U equals F over J. So that's just a change of variable. And associated with this PDE, we have the boundary condition. That is a du omega equals omega star, because du is a mapping. So you map everything from omega to omega star, okay? And therefore, in order to study regularity of the optimal mapping T, that's equivalent to the regularity of this solution to this kind of boundary problem, okay? So once you have regularity of the function U, certainly you have regularity of the optimal mapping T, okay? Now let's see what kind of regularity do we have. In dimension 2, it was first proved by Delanoy in 1991, and then by Urbis from Australia, 1997 for arbitrary dimension. And they told us, as far as both domain, initial domain omega, target domain omega star, uniformly convex and smooth, then if the density function is C infinity, then the solution U will be C infinity globally. So once we know the C infinity optimal mapping T, certainly it will be smooth, okay? In 1996, Caffelli proved the global shoulder. So Caffelli says, as far as both domain uniformly convex with the C2 boundary and density function, if the density function is C alpha, then the solution will be globally C2 alpha. So once we have the global shoulder, and certainly we can use the bootstrapping, and we go higher and higher and higher, okay? Now, the long story short, if the domain is uniformly convex, that means the curvature has a positive lower bound, everything is good, okay? We know that. And if the domain is not convex, so that means curvature somewhere could be negative or equal 0 or something, then not equal 0. So if the domain is not convex, that means curvature somewhere is negative, then we can construct counterexample to show the solution is not even C1. So that means optimal mapping T not continuous. And so the question is, how about a critical case? So critical case is the domain is convex, but not uniformly convex. So that means somewhere the curvature could degenerate to 0. So in a joint work with Shibing Chen and Xu-Jia Wang, we proved that as far as both domain is convex and with C11 boundary, if the density function is linear continuous, then we have the estimate on the, the modular continuous, estimate on the modular continuous for a second derivative. And that implies if the density function is C alpha, then we have the global shoulder. So the solution U will be C2 alpha, and then you can go higher and higher. And related result was given by Savin and Huiyu in dimension 2. That's for arbitrary convex domain. And when the density function is constant, they prove the solution U will be globally W2P for any P less than infinity. And last year, a very nice result by Collins and Tone, the organizers. They reduce the regularity for the boundary. They only assuming the boundary is C1 alpha. Then if the density function is C alpha, then they have the global shoulder as well. Then after that, you can go higher and higher. So it's pretty nice. All right, so that's a very brief introduction about optimal transport. And then we move on. We look at optimal partial transport. So optimal transport, that means you're trying to transport everything from omega to omega star. But the partial transport is actually we only transport, a part of it. Okay. in reality, that means your supply is equal to 1, and your demand is strictly less. You do not need everything from omega. You only need part of it. Okay. So the question is, how can we decide? How can we decide which part is going to be transported and which part do not? Okay, you have to divide the domain into 2 parts, and certainly this hypersurface is called free boundary, and it depends on how much do you need. It depends on your demand. If your demand is also equal to 1, then that's complete optimum transport. You have to transport everything from here to here. Okay, so that means free boundary is gone. And if your demand is 0, there's nothing to transport, right? It's also empty side. So if the M is between 0 and 1, and somewhere in between you have the free boundary. Okay. Such a model has many applications. The fancy one is in AI, the natural language. So for example, imagine you have a very long essay or very long article, 20 pages, 200 pages. You're very busy, you do not have time to read it, right? So you put it into ChatGPT and ask, can you give me a summary, right? So the ChatGPT has to decide which word is going to be picked up and which word we can just ignore it, right? So that is a free boundary. You have to decide which is more important to be transported and which is not, okay? And in Robert McCann's lecture, he also introduced application in financial mathematics as well, okay? It's quite interesting. But in mathematics, we're trying to understand what kind of regularity such a free boundary could be. I mean, how smooth it could be, okay? All right, so similar as optimal transport, in this case, we actually, we also know the optimal mapping T that depends on the M, okay, depend on your demand. This optimal mapping T is also given by a gradient of some convex function. And that convex function push forward Fm to J. Fm is the restriction of the function f over the active region. Okay, so active region, that means the region you are going to transport it. Okay. And in 1992, Caffarelli actually told us, as far as the target is convex, then the solution U will be C1 alpha locally. Okay, there's no other restriction, no other assumption on the domain. As far as target is convex, then solution U will be C1 alpha locally. But however, this is not sufficient to study the regularity of the free boundary. Because we claim the free boundary, in order to study the free boundary, we need to know the regularity of the function U up to the free boundary. So the interior regularity is not enough. We have to know some kind of boundary regularity. And why is that? A key observation in this problem, which is given by Caffarelli and McCann, so-called interior ball property. So interior ball property, that means if you look at a point x on the free boundary, and the target is tx in omega star, and then you draw a sphere centered at the tx, and the radius is the length between x and the target, you draw a sphere. That sphere has to stay on one side of the free boundary. So that is called interior ball property. So that means such a sphere cannot cross the free boundary. It has to stay on one side. So every point you have a supporting sphere. Every point you have a supporting sphere. Okay. So basically it tells you the free boundary somehow it's already semi-concave, semi-convex, depending on which direction you look at it. Okay. It makes sense, right? It makes sense. Why does this make sense? By contradiction, I mean, this picture is wrong, right? This picture, I'm going to claim this picture never happened, okay? So imagine if the sphere crosses the free boundary, then it will contradict with the optimality. Why is that? If the sphere crosses the free boundary, then instead of the mapping X, the black dot, to the target, why don't you map in the red dot? Because the red dot is save lots of the distance, save lots of the energy, right? So that will contradict the optimality. I mean, heuristically, it's not a proof, but heuristically, we can understand in that way. Okay. So therefore, we know the interior ball property. Every point we have a supporting sphere. Now, if the solution U is C1, what do we know? We know that because on the free boundary, you have a supporting sphere on one side. So therefore, the normal direction assuming it's well defined. Okay, so the normal direction will perpendicular with the free boundary. So that means the normal direction is exactly given by the gradient of u minus x and normalize it. Okay, gradient u is the target. So that's exactly tells you this vector gives you the normal direction. Okay, so once we know that, it implies in order to study regularity of the free boundary, that's equivalent to study regularity of the solution u. So if u, let's say if u is C3, then the gradient will be C2, then the normal vector field will be C2, then free boundary will be C3. So regularity of the free boundary exactly the same order as regularity of the solution u. Okay. Okay, so that's an introduction about free boundary. And the first result in this topic, very important one, it was proved by Caffelli and McCann. So they show that as far as the two domain omega star uniformly convex and separate from each other, then if the density function is bounded from below and above, then they prove the free boundary will be C1 alpha for some alpha between 0 and 1. But their argument is by compactness, so there's no explicit expression estimate on the alpha, but we only know the alpha is between 0 and 1. Okay. And later on, Figali and his student, PhD student Indri, they consider when omega and omega star has some kind of overlap. So if omega and omega star has overlap, then Figali proves that as far as the free boundary do not touch the common region, then the free boundary will be C1, locally C1. Then Indri improve from C1 to C1 alpha. So that means as far as the free boundary do not touch the common region, then the free boundary will be locally C1 alpha. Okay. So that's a previous regularity result. However, we are more curious about the higher order regularity. Once you move to the higher order regularity, then you can use the bootstrapping, go higher and higher. But unfortunately, the difficult part is actually coming from the loss of the convexity, because the free boundary in general is not convex. If you are lucky, it's convex, then you have the optimal transport from a convex domain to convex domain, then it's well known, right? But unfortunately, the free boundary, it could have a zigzag, it could be very wild, right? There's no convexity in general, so that causes a lot of trouble. So finally, a few years ago, in another joint work with Shibing Chen and Xu-Jia Wang, we managed to obtain the higher order regularity for free boundary. So what we prove is there's no assumption on omega as far as omega is bounded. That is good enough. But we need to assume the target is C2 and uniformly convex and separate from each other. And in that case, if the density function is C alpha, then we manage to prove the free boundary will be C2 alpha. Okay. And how do we overcome such a difficult causing by the loss of the convexity? Is actually we're trying to prove the so-called obliqueness estimate. So what does obliqueness estimate means in this talk? I also heard obliqueness estimate a few days ago in some talk, but maybe there's some relationship. But here, by obliqueness, I mean, if you look at the 1 point on the free boundary, it has a normal direction nu. And if you look at the target, it has a normal direction nu star. So obliqueness means the angle between nu and nu star, the theta, is strictly less than pi over 2. Okay, that is called obliqueness. I mean, we can compare such an obliqueness estimate with the Hofleimer for Dirichlet boundary problem, right? So Hofleimer says, I mean, for arbitrary function in a domain, if the function achieves the maximum on the boundary, then we know the normal derivative will be bigger or equal than 0, right? But Hofleimer tells us if we have one extra piece of the information such that such a function, not arbitrary function, it's a solution of a nice PDE such that it's a uniformly elliptic PDE, then Hofleimer prove the normal derivative will be strictly positive. Okay, so similar as here, if we know this domain is a gradient mapping of a convex function, then such an angle is always bigger, less or equal than pi over 2. That's due to the monotonicity of the convex function. And But in this case, it's not an arbitrary convex function. It's a solution of Monge pair, right? So we have one extra piece of information from the PDE. So by using that PDE information, we can improve the inequality to be strict. Okay, so it's very similar as a Hopf lemma. And we know that for Dirichlet boundary problem, once you have Hopf lemma, you can construct the barrier function, then you can prove the boundary regularity, right? So similar here. As far as we have the obliqueness estimate, then we can manage to obtain the boundary regularity as well. Okay, so this is a crucial part. Now let's see how we are going to obtain the obliqueness. Okay, so I just change the language a little bit. So in order to prove the angle is strictly less than pi over 2, it's equivalent to say if nu is a normal vector, nu star is a normal vector, then the inner product is strictly bigger than 0. Okay, and due to the monotonicity, we know it's always bigger or equal than 0. But now we're trying to improve it to be strictly bigger than 0. Okay. By contradiction, okay. If such an obliqueness fails, we can assume obliqueness fails at the origin. So origin is a 1 point on the free boundary. Then in dimension 2, the picture will look like this. I mean, in this presentation, we assume everything in dimension 2, but argument is working for arbitrary dimension. So dimension 2 is easy to draw a picture. Okay. If obliqueness fails at origin, then by changing coordinate, we can assume the normal direction is vertical. It's going upward. It's a E2, and on the target of the origin, the normal direction is horizontal. It's E1. Okay, so the picture will look like this. And locally, the free boundary around the origin, the free boundary will be given by x2 equals a function rho x1. Okay, and that function locally describe the free boundary. And around the target, because we're assuming the target is uniformly convex and C2, so around the target, we know that the boundary locally is given by another function rho star. And that function rho star is quadratic function plus some extra term, a lower order term or higher order term, depending on how you define it. So it's a quadratic function plus something extra. Okay. Now we have sort of an estimate on the function rho. So that means the local geometry for the free boundary. So first, by using monotonicity of the convex function, of the gradient of convex function, we can prove the function rho on left-hand side part is non-negative. So that means the free boundary on left-hand side part, it has to go up. It cannot drop down. So, I mean, it's also easy to, I mean, it makes sense. It's easy to understand because your target, everything here is on right. So somehow it pull up the free boundary. The free boundary on left-hand side part, it cannot drop down. Okay, it has to be non-negative. So that makes sense. But you have to, in order to prove precisely in mathematics, you have to apply the monotonicity. Okay. And even better, by using the interior ball lemma, we can show that on left-hand side part, this function is almost quadratic. It's quadratic plus some extra term. And this R is the distance between 0 and the y. It has a positive lower bound. So everything here is fine. It's a quadratic function plus some extra term. Okay. So that describes the left-hand side part of the free boundary. And right-hand side part of the free boundary, we also have the lower estimate. So that means it cannot drop too much. It can be negative a little bit, but cannot be too negative. Okay. All right. Now, okay, once we know the picture looks like this and have some local geometry, we're trying to blow up. It's a very standard technique in PD, we're trying to blow up. But in this case, blow up, that means we are going to, instead of looking at function u, we actually look at the level side of the function v. So remember, u is a potential function in optimal transport, and we also have the duality, the dual potential, that's coming from the Kontorovich duality formulation, right? You have a u, the gradient of u is optimal mapping from omega to omega star, then the gradient of v is the reverse, is from omega star back to omega, right? So they are the under transform of each other. So, I mean, somehow it looks like a twins. Once you have information about the function u, then you certainly have information about function v. So in order to study, vice versa, right? So in order to study the regularity of function u, and we turn the other way. we are going to look at the function v, the twin brother. So you may be wondering, why do we look at v instead of u? And certainly, if you look at the function u, the domain, there's no convexity. But however, if you look at the function v locally, you still have convexity domain, right? So that makes more sense. And by change of coordinate, we can assuming the function v and the function u, it equals 0 at the origin, and the origin is a local minimum, a global minimum. So let's see. So what does level set means? If we have a function, convex function, and at origin it's a minimum, now we lift this tangent plane by h. Okay. So here is h, and we cut the graph of the function v. You cut the graph and do the projection, you have a convex domain here. So that is called level set, right? So if such a function v is strictly convex, you reduce the height h, let h go to 0, then the level set will shrink and shrink until, oh, sorry, I have to shift everything a little bit. So it's shrink and shrink until it becomes a single point, okay? I have to shift a little bit, okay? So in order to study the regularity of such a convex function, in other words, it's equivalent to study how quickly the level set is shrinking, right, for convex function. Imagine if the level set shrink very fast, so that means the convex function here is very sharp, okay? But on the other way, if the level set shrink very slowly, very gently, so that means the convex function here is very flight, I mean, tandem flight, very, 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 very gentle, right? So that's how the regularity comes from. By using the iteration, you have different kind of estimate. Okay, so in order to study the regularity of function v, a convex function, we need to understand the geometry of such a level set. Okay, so long story short, so if we consider a level set of the function v, first we can prove such a level set is actually balanced. So balance, that means the origin somehow it's very close to the middle. Okay, so the upper part and the lower part, they're almost the same. Okay, I mean, I don't want go too much details, but in Munchen pair, you have to define two different kind of level set. One is the height one, the other one is the center section, right? But they are equivalent somehow. So I want to skip that one. So the first property we are talking about is balance. And then we try to estimate the geometry. So that means what's the length vertically and what's the length horizontally. So by using different kind of technique, we know the length, vertical length is almost h to the power 1/3. So h is the height, okay? And the length, horizontal length is almost equivalent to h to the power 2/3. So once we know the geometry, it tells us using such a Fn transformation, using such a matrix, we can blow up, we can change the level set to be almost equal to a unit ball. Okay? All good? Okay. So the good thing is the power is 1/3 and 2/3. Why it's good? Because once you know it's 1/3 and 2/3, such a Fn transformation, it preserves quadratic curve. Okay, the power exactly quadratic. Okay. So the Fn transformation is actually preserved quadratic boundary. So that means we can keep blowing up. So every small h we blow up, every small h we blow up, and in the limit, we are going to look at the limit profile. Because quadratic part will be preserved. So therefore, originally, we know the free boundary on left-hand side part is quadratic function plus some extra term, the lower order term. Okay. So once you go to limit, the extra term will vanish. It will gone. So on left-hand side part, the free boundary will be exactly equal to the quadratic function. Okay. And for the target, because we're assuming the target is quadratic plus extra term, and in the limit profile, we can prove the target again is exactly given by quadratic function. Okay. And certainly the Munchen pair will be determined d2v equals the constant. But that constant, that means inside domain, it equals 1, outside equals 0. Okay. So that's a limit profile. And now we need to use the smoothness of the function v of the limit potential function. And in order to handle this, we have some kind of observation. Okay, by using monotonicity, we know the upper part of here corresponding to the left part, and the lower part corresponding to the right part. Okay, now we focus on the upper part. If we focus on the upper part, it's a quadratic curve. It's mapping to the left part. It's also quadratic. So therefore, we know it's an optimal mapping. It's an optimal transport from a very nice domain to another very nice domain. So you can use approximation to prove such a limit function, such a limit v is actually smooth. I mean, at least it's smooth on the upper half. Okay, don't touch the lower part. So upper part is smooth. And once we know the smoothness, we can derive a contradiction. So how we derive the contradiction in the limit? We define such an auxiliary function w. So w is given by v2, so that's a partial derivative, partial v, partial y2, okay? So w is equal to v2 plus v minus y2 v2. If you work in Monge pair, this probably looks very familiar to you because such a function is a solution of the linearized Monge pair, right? And then over each horizontal line, we define the w underbar to be the infimum of the w along this line. So therefore, the w underbar will be a single variable function. Okay, so w is a two-variable function. It's a multi-variable function. But once you define the infimum along each horizontal line, so the w underbar will be a single variable function. It's only depend on the t. T is from 0 to a very small number. Okay, locally. And on one hand, because w satisfied the linearized Monge pair and is homogeneous, so we can use a maximum principle to prove the w underbar, this single variable function is concave. It's a concave function, okay, by using maximum principle. And on the other hand, we have the decay estimate. So decay estimate tells us such a single variable function is pinched between 0 and the quadratic. It's pinched by, say, t0. So that means when the variable approaching to 0, the derivative approaching to 0, okay, because it's quadratic, okay. Now you have a single variable function. The single variable function is concave and derivative at the origin equals 0, so that means the function can only going down. It cannot going up, right? It's only going down. So that means such a single variable function in a small segment, the value is non-positive. But however, on the other hand, we know it's non-negative. So that means in a small segment, such a w underbar is constantly 0. Okay, one side is due to maximum principle, the other one is a decay estimate. But such a decay estimate is not trivial. We have to go much. It's very technical. Some kind of estimate here. Okay. So this w underbar is constantly equal to 0 in a small segment. That gives us a contradiction. Why it gives us contradiction? Because we know the w is actually strictly positive due to the strictly convexity of the function v. So that's how the contradiction comes from. Any question? Okay, go ahead.
In terms of the right-hand side, so you're only using that it's point-wise continuous at the domain point and target point?
Yeah, point-wise, yeah.
A constant of the blow-up.
Yeah, that's right. Okay, so such a contradiction, it occurs because we assuming obliqueness fields, right? So by contradiction, we obtain the obliqueness. So once we have obliqueness, life will become much easier. So I skip the rest of the part. So once we have obliqueness estimate, similarly, as far as you have the Hopf lemma, you can construct the boundary estimate. Okay.
Counter examples to obliqueness when the right-hand side is not continuous.
Say that again.
Do you have counter examples to obliqueness when the right-hand sides are worse?
Good question. No, at the moment I don't think anything, but I believe we can try to construct one. But I don't know. Yeah, at the moment. Okay. Now let's move to a different question. Okay. Previously, we understand the free boundary, the regularity free boundary. Now I try to understand how does the free boundary touch the fixed boundary. Okay, because the free boundary is the red curve, and originally you also have the fixed boundary, so they will touch each other. How they touch each other? They could touch each other very gently, right? Very nicely, such that you have a cusp. Or they could just cross each other. What's that called? Transversely, right? So you have an angle, right? So we're trying to understand what's the case, and why do we care? Why do we care the cusp or transversely? That's because in order to study regularity of the Munchen pair, we know that doubling property is crucial. So doubling property is very important. So what does doubling property means? That means if you have a domain, you look at the boundary point, you use a ball to bite the domain. Okay. After you bite the domain, you have a volume. Then you use a smaller ball, a half ball, to bite the domain. You have another volume. So the doubling property says the volume beaten by the ball is actually bounded from above by the volume beaten by the half ball, okay, with a uniform constant. So that's a doubling property. It's very crucial for Munchen pair, for regularity of the Munchen pair. Now, imagine if you have a cusp, this doubling will fail, right? Because once you have the cusp, the half ball will, the volume beaten by the half ball is shrinking too fast. Okay, so that means the doubling will fail. So cusp is not good in this case. We're trying to rule out the cusp side. But the cusp side, about the size of the cusp, I think the first one is given by Indri in 2013. He actually tells us the Hausdorff dimension of the cusp is at most n-2. Somehow it makes sense because the whole domain is Rn, right? So the boundary, this domain is in Rn, so the boundary is n-1. The cusp is the bad side. So bad side is n-2. So somehow, we can think in that way. And very recently, in joint work with Chen and Wang, but this Wang is not Xu-Jia. It's not Xu-Jia Wang. It's another Wang. Okay, it's a very popular family name.
Chen is still Shibing Chen.
Sorry, yeah, Chen is still Shibing Chen. Chen is a popular. All the family name is popular. So the Chen is Shibing Chen, but Wang is a student. Currently he's doing the postdoc. So it's not Xu-Jia. So what we prove is a cusp is actually does not exist. It's not only dimension, Hausdorff dimension is small, it's actually empty side. Okay. So empty side, our assumption is as far as both domain is bounded and strictly convex and they separate from each other, and as far as the density function is bounded. Now we do not need any continuous, okay? As far as the density function is it's bounded from below and above, we prove the cusp is actually empty. If there's no cusp, that means the active region U is globally Lipschitz, okay? And how do we rule out this cusp? And again, by using the powerful interior ball property. So interior ball, that means for any point on the free boundary, you draw a sphere. The sphere has to stay on one side of the free boundary, okay? By using such a nice property, we can rule out the cusp. The calculation, the proof is very elementary, I would say. Okay, let me show you the proof. Okay, so the proof is by contradiction. Let's assuming we have a cusp. We're assuming we have a cusp on the free boundary and the touching at the intersection point between the free boundary and the fixed boundary, there is a cusp. Then what we are going to do by changing a coordinate, we assuming the picture looks like this one. Okay, the free boundary, the normal direction is vertically, and then you have a target y0, that's a target of the origin. So what we are going to do is we consider a small neighborhood, a small ball around the target, the B epsilon. Then the volume here, we can prove it's epsilon with the power n to the power n. It's calculus, okay? Because we're assuming that this curve, this boundary is smooth, and then you consider a B epsilon, so the intersection, the volume will be epsilon to the power n. Because it's optimal transport, we have the balance condition. If the volume here is epsilon to the power n, the volume in the pre-image, it should also be epsilon to the power n, okay, by using the balance condition. And now we trying to estimate the volume on the pre-image. From the interior ball condition, what do we have? We can draw a purple ball, consider arbitrary point P in this small region. we can draw a purple ball, a purple sphere. So the target here and the initial point is here. You draw a purple sphere. The purple sphere will be, everything will be above the free boundary. It's on one side of the free boundary. So that means the distance between P and Q is less than the distance between P and origin. Okay, so this inequality is coming from the interior ball property. Now we just play with this star inequality. If you decompose such an inequality along En direction, you can estimate what's the length of the Qn. So that means the length along the En direction. We have to estimate the Qn is bounded by epsilon square. Okay, I mean probably we do not have enough time. Otherwise, I can show you how to do the calculation. But it's a freshman calculation. It's very easy. So along the En direction, we can estimate the length is bounded by epsilon square. Now you decompose such an inequality star along the other direction. Along other direction, by using the Cauchy-Schwarz inequality, we can prove along other direction it's actually bounded by epsilon. So that means the pre-image is bounded by a box. That box, the length here is epsilon square, and the length otherwise is bounded by epsilon. So the volume of the box is epsilon to the power n+1. That's a contradiction, because the volume is much smaller than the volume here. It contradicts with the balance condition. Okay, if you choose epsilon small enough. So that's how we rule out the cusp. So cusp do not exist. Okay, so once we prove there's no cusp, then we can go further. We can prove the free boundary is almost C11. So almost C11, that means the free boundary, I mean the global regularity. The free boundary is almost C11, that means the free boundary is actually C11 minus epsilon up to the intersection point. Okay, for arbitrary epsilon smaller than 1, but it's never achieving 1 because we have counterexample. I'll show you later on. So this is almost C11. And how to prove this part? Again, the key ingredient is obliqueness, but it's comparing to obliqueness before when we studied the free boundary, it's a little bit slightly different. Why slightly different? Because if you look at the intersection point, here, you have two normal vector. One is a normal to the free boundary. The other one is normal to the fixed boundary. So obliqueness, that means the normal of the free boundary and the normal of the target, the angle is less than pi/2. And simultaneously, you have to prove the normal of the fixed boundary and the normal of the target is also bounded, strictly bounded by pi/2. So you have to prove two obliqueness simultaneously holds. Okay, so you have 3 vectors. That makes sense? And even worse, because it's in higher dimension. You have 3 vector. No one tell you the 3 vector is in the same plane or not, right? The 3 vector could be somehow like this x, y, z coordinate, right? If it's in the same plane, that's life is much easier. But however, we have to handle many different kind of cases. Okay. Okay. So that means we have to rule out the case by case. So the first case is obliqueness fields on the free boundary. And second part is we need to rule out obliqueness fields to the fixed boundary. So you have to rule out this case by case. So for case 1, because we already know there's no cusp, so therefore the normal direction of the free boundary and normal direction of omega, they span a 2-dimensional space, a hypersurface. And the rest of the direction will be n-2 space. That's a H prime. And again, you have to consider the normal of the target is belong to H prime or do not belong to H prime. Okay, I mean, that's actually there's more than 2 cases. There's a sub cases as well. It's quite technical, so I don't want make you feel boring, but I just tell you the idea. The idea is once we know what happens by contradiction and by using the blow up, every time, as far as you have the control of the sub-level site, as I mentioned here, as far as you have the control on the geometry of the level site, then you know what kind of FN transformation can do your job, can do the blow up, right? Then you take the limit to look at what's the limit profile. So in case one, the limit profile will look like the target become, okay, this is very similar to the word I learned this week. It's called splitting theory in geometry, right? I mean, originally you have a higher dimensional hypersurface. Now in the limit profile, it become a two-dimensional, okay? So the convex domain is exactly a two-dimensional curve and across all the other n-1 direction. Okay, it's a splitting. So we can prove similarly here. In the limit profile, the higher dimension problem is also the domain also satisfies the splitting theory. So by splitting theory, we can reduce the dimension. So higher dimension problem become a two-dimensional problem. Once we have a two-dimensional problem, we have a different way to derive the contradiction. Okay, so that's a long story short. I don't want to go into much details. So that's another case, the case 2. But if you are interested, we can discuss this afterwards. Okay, and similarly, once you have the control on the level side, then you keep blowing up, and to figure out what's the limit profile, and the limit profile will satisfy splitting. Once you have the splitting, then you reduce the dimension. Once you reduce dimension, you can derive a contradiction. Okay, so that's the idea. All right, now I want to show you a counterexample because we proved almost C11. Almost C11, that means the free boundary up to the intersection with a fixed boundary. It's C11 minus epsilon for arbitrary epsilon, but it never achieves C11. So this counterexample was due to Salvin and Huiyu by using the blow up and the maximum principle. So the example goes like this. Okay, imagine the initial domain is a unit ball in R2, and the target is very small. It's the B 1/100. Okay, it's a very small disk here. Then you do the optimal partial transport. So optimal partial transport, you have a free boundary. Free boundary will be symmetric, because everything here is symmetric. So you have the free boundary. Now we look at what happens at the intersection. At the intersection, by changing the coordinate, it will looks like exactly like this one. So once you have obliqueness, you can assume the target is in the upper half space, and the domain with the free boundary, it forms a wedge, it forms an angle. So in geometry, I believe this is also called tangent cone, right? So the tangent cone on the domain, it has an angle. That angle is bigger than pi/2 and smaller than pi. Okay, you have a tangent cone looks like this, and the tangent cone of the omega star, that's exactly the Hafer space. Okay, because we're assuming here everything is C2 and uniformly convex. So after you blowing up and become a Hafer space. Now by contradiction, if we have the solution U that is C11, assuming solution U is C11, but it's not true, right? By contradiction, if it's C11, we can use the standard quadratic blow up. This quadratic blow up doesn't change the second derivative, okay? And especially when H goes to 0, and the limit will satisfy, C11 doesn't change. The limit will satisfy a Monge pair with the right-hand side part equals constant 1. Okay, the constant 1 is because we're assuming the density is Lebesgue density. Okay, so the limit will be equals the Monge pair with constant 1, and it mapping the upper half space to a wedge. This never ever happened, right? Why? Because once you have the Monge pair with a constant, then the second derivative will satisfy maximum principle. And second derivative satisfies maximum principle. If the maximum occurs inside, that's a contradiction. If it occurs on the boundary, we can do a reflection. After you do reflection, the boundary point again become interior point. So that's a contradiction to maximum principle. So every direction, the second derivative is a constant. So therefore, such a potential function, the limit potential function, will be exactly quadratic function. But quadratic function cannot map a half space into a wedge. It has to map a half space to another half space, right? So that's a contradiction. Okay, so it's almost C11. It's a sharp. I have one. Okay. 5 more minutes. 15. Wow, you're so generous. Yeah.
avoiding that.
It's okay. I mean, I try to speed up. Now the third part of my talk, we are going to look at a slightly different model in optimal trend plot. Okay, it's quite interesting, so that's why I want to keep introduce this. Okay, so in optimal trend plot, there's a famous example constructed by Caffarelli. I mean, if you look at any lecture notes, you will see this example. So Caffarelli says, if the domain omega is a unit disk, and the target is two half disks and separate from each other, right? Then explicitly, the potential function is equals quadratic function plus x1 is this direction, plus absolute value of x1, okay? I mean, if you calculate what's the gradient is identity mapping plus the sum of x1. So if you are on right-hand side part, you move rightwards by 1 unit. If you are on left, you move leftwards by 1 unit, right? So that gives you the optimal mapping. And for such a potential function, it's not differentiable on the singular set. Where is the singular set? That's exactly x1 equals 0, right? On this singular set, such a potential function is not differentiable, right? So that's an example from Caffarelli. So what we're trying to do is we consider initial domain is one piece, and target you have two pieces. Okay, it's not necessary to be half disk and disk. I mean arbitrary two separate target. So in reality, you can imagine you have some kind of product in Boston, maybe. You're trying to move half of them to Toronto and half of them to New York City, maybe. So you have to decide which part goes to Toronto and which part goes to New York City, right? So in between, you also have a hypersurface to divide the whole domain into two parts, okay? You can call this singular set because the potential function will not be differentiable. Similar as Caffarelli example, the potential function will not be differentiable along this hypersurface. Okay. So we're trying to understand in mathematics. We're trying to understand in general case about this singular set, or we can call it free boundary or singular set. It's up to you. We're trying to understand how smooth it could be. So that makes sense. In Caffarelli case, it's flat, right? There's nothing to talk about. But now I'm looking at more general case. So we're trying to understand what's the geometry and what's the regularity for this hypersurface. This was proved in a joint work with Shibing Chen, the same chain. So in last year. So what we prove is, again, there's no assumption on omega. As far as omega is bounded, we will be happy enough. So omega, we do not assume any convexity. But on omega star, we assuming it's a union of two separate convex domains. So omega 1 star and omega 2 star. And then we can show as far as the density function is bounded from below and above, then the singular set will be C1 alpha for some alpha between 0 and 1. Okay, this argument, again, by compactness is similar as a Morgan pair, so there's not too much to say. But if we assuming additionally the target is C2 and uniformly convex, then we can prove the higher order regularity. So that means if the density function is C alpha, then a singular set will be C2 alpha. Okay, so that's how you divide your product in Toronto into two parts. You using a very smooth curve. Others are using zigzag. Go ahead.
The singular set is has codimension 1.
Codimension. Yeah. I mean, as far as you have regularities, certainly.
Other types.
What do you mean other type of single?
Like codimension 2, codimension 3.
No, it never happened. It never happened. Yeah. Okay. So this problem, as I mentioned at the beginning, is very similar to the study of the regularity of free boundary. Because we have similar difficulty, there's no convexity. And in this case, unfortunately, we do not have interior ball property. As you already seen, interior ball is very powerful. It's very useful when we study free boundary. But in this case, unfortunately, it does not hold. We do not have interior ball. Okay, so the problem becomes even tricky. But the key point, again, is to trying to prove obliqueness. Because if you want to study the regularity of the free boundary, you have normal direction. And this point on the free boundary is going to be split. because it's on the boundary, right? If you're standing here, everything goes to Toronto. If you're standing here, everything goes to New York City. But if you standing somewhere in the free boundary, in the hypersurface, you have to split it, right? So every point here, you have a normal direction, and correspondingly, you have two targets. You have two normal direction on each. So obliqueness, that means you have to prove obliqueness holds in the first target and obliqueness simultaneously holds on the second part. And by that, you can, once you have such a simultaneous obliqueness, then you can prove the regularity and you can go higher. Okay. And similarly, because we have three vectors may not necessarily stay on the same plane, right? You have to consider case by case. So here we need to consider three cases. So obliqueness field simultaneously, but however, the three vectors in the same plane, and the obliqueness fields, and they are not in the same plane, coplanar. And all the obliqueness fields on one target, but it's very nice on the other target. So that means we have to rule out all three cases one by one. I don't want, take too much time because we have the morning tea comes. So, but the idea is quite similar. I just tell you the rough idea. The rough idea, again, we use blow up. But in order to apply the blow up, you have to understand the geometry of the level side. So the step one, you have to estimate on the level side to see along each direction what's the size of the level side. Once you have the geometry of the level side, then you know the FN transformation or the matrix. What kind of matrix can do your job, can do the blow up, and then you keep blowing up. So in case one, that's nice because everything is coplanar. So three vector coplanar. So if obliqueness fails, the picture will be given somehow like this one. You have a target above, you have a target below. And once you have the size of the geometry, you keep blowing up, the two targets will become far and far and far away. So if the two targets become far away, it stretch the free boundary to be more flat. It's flatter and flatter and flatter, okay? But that gives you contradiction. Because if the free boundary is too flat, you just trace it back. So, okay, you have a potential function here, you have potential function here. Potential function here, all the gradient is on right-hand side part. So that means if you trace it back in the opposite direction, the potential function will be going down because the gradient is on right-hand side part. So that will contradict with the convexity. Okay, so that's how we rule out the case one. And for case two and case three, it's very similar. You have to have first derive a precise geometric control to see what's the size of the level side. And then you have the affine transformation to do your job, to do the blow up job. And in the limit profile, okay, I just skip a little bit. So in the limit profile, again, you have to show the splitting. It's a splitting theory, right, in the geometry. So higher dimensional domain will be reduced into a two-dimensional domain. So how to describe that? That's a product, right? So the convex domain will become a convex curve and the product and times all the other directions. So it's a splitting. Once we have the splitting, we can derive the contradiction. And similarly, case by case, you can, along the same idea, you play the same game. Okay. If you are interested, I can go much details afterwards. Okay. I think that's all I want to talk. Thank you.